we have the following situation. I have a sample x1 through xn. I have a statistical model, that is, I've made some assumptions about the joint distribution of x1 through xn viewed as random variables. Among these assumptions, I have at least one unknown parameter that we denote by theta, and I have created an estimator of theta that I denote by theta hat. The important part here to remember is that theta hat is a random variable before we observe the sample. This is the typical setup in statistics, and there is a useful way of thinking about this setup. You can think of this as a game between you and an opponent that we can call nature. So in this game, nature says something like, I am going to simulate a sample from some distribution. I'm not going to tell you what this distribution is, but I'm going to give you the sample. I'm going to give you these numbers, x1 through xn. I am also thinking of a number that I'm going to call theta, and your job is to guess which number I am thinking of by using the sample. In this game, the number that you are supposed to guess, theta, has been used in the simulation of the sample, and you know exactly how it has been used. For example, you may know that in the simulation, the expected value of each sample point is this unknown number, theta. So you are faced with a bunch of numbers, and from these numbers, you are to come up with a guess of theta. So what you do is that you design a rule that will provide a guess from the sample. The rule is simply based on feeding the sample into a function g, and the output of this function g, that will be your guess. This means that your guess will be random as well, as it's based on numbers that are random. Your guess, theta hat, will have a distribution. What this distribution looks like, well, that depends on the distribution of the sample, but also on the rule g that you use. So we have some density like this, f of theta hat. If the density of your estimator looks like this, then most likely your guess will be somewhere in this interval, with the smaller probability that your guess is out in the tails. The estimator, being a random variable, will have an expected value. That's the expected value of your guess. We can think of the expected value of theta hat as the average guess that you will provide if we play this game repeatedly. If this expected value should be equal to the unknown parameter, the number that you are trying to guess, then that is pretty good news. It means that your rule, in a sense, is on average correct. You have then created a nice estimator, and such an estimator will be called an unbiased estimator. So the definition of an unbiased estimator is that the expected value of the estimator should be equal to the parameter that we are attempting to estimate. Since we are using estimators to draw inference about unknown parameters, being unbiased is a nice property. In terms of the picture, my estimator is unbiased if theta is the expected value. Of course, this does not mean that when you play this game once, that your estimator will be equal to theta. If you have 95% of the mass of the PDF, say in this interval, then you can say that with 95% probability, your guess will be in this interval, and with 95% probability, it will at least not be too far from theta. So how do we know that our estimator is unbiased or not? Well, that is based on the statistical model. Remember, we do make assumptions about the joint distribution in the statistical model, and whether our estimator is unbiased or not depends on these assumptions being satisfied. For example, if this is my sample, then this is my statistical model. I assume a random sample, and I assume that each observation is drawn from a normal distribution with the sample mean mu and a variance sigma square. This is the information I can use to check whether my estimator is unbiased or not. So for example, the sample average will be an unbiased estimator of mu. We know that the sample average has this property that its expected value is equal to mu whenever I have a random sample. Given that the assumptions in our statistical model is satisfied, the sample mean will be unbiased. Of course, if I don't make any assumptions, if I'm just given a sample, then I will never be able to show that an estimator is unbiased. In the same way, we know that the expected value of the sample variance is sigma square, and that means that S square as an estimator of sigma square is unbiased.